I feel like I'm a bit of a math machine. I'll be done another unit. So we are looking at field and poster problems. So there's two field problems, I think, and two poster problems. The poster ones are a little more complicated than the field problems. You may have had some experience with field problems or some field problems in the quadratics unit of your grade 10 course or your grade 11 or both. Okay, so field problems. Again, I'm going to draw a picture. So it says a lifeguard marks off a rectangular swimming area. So that's pretty easy. Rectangular swimming area with 200 meters of rope using the shore as a natural boundary. So I got cocky because I don't need rope along here. So I've actually only got 3 sides that need rope. So I'm going to call these two X because they would be the same dimension and this one Y. So I hope you can see where we're going with this. We're probably going to have to isolate, so I let Y be the 1 and X be the thing that there's 2 of, so a Y is easier to isolate. And it says that that takes 200 meters of rope, so I can dig out my red pen and say that 2 X's and a Y is equal to the 200. And I'm just going to assume that I have to get y by itself. So I'm going to take the 2x across the equal sign and subtract it. And then over to blue, so I don't need a let statement because I've got a picture. Over to blue, it says, what is the greatest area? So I'm trying to maximize the area. And area for a rectangle, regardless of whether it's missing its fourth side or not, is length times width. So that's x times y, or y times x. And then I'm going to take this, and I'm going to plug it in. So I'm going to call it max. So x times fancy y. Because I don't want to do the product rule, I'm going to multiply this out. And I don't have any like terms to collect. So I'm going to leave this quadratic out of order for quadratics because all I'm going to do now is take the derivative. So this is a negative quadratic, so this is an upside down parabola, so I should actually have a maximum. So this is something you could have done in grade 10. So time to actually take the derivative. 200, oh, we can't make that look like a double tick. (200 minus 4x). Make sure it equals 0 at some point. So you have to tell me you're taking the derivative so I know what's happening. You have to tell me you're equaling 0 because that's when max mins happen. And then, so, like, yes, I see that this might be a waste, and if you wanted to put your equal 0 here, I would not lose my mind, but somebody might. So let's get rid of that. So bring the 4x over and make it positive. Divide by 4, divide by 4. And I have x is equal to 50. Read the question. What is the greatest area? So I actually don't care what the other dimension is. I only care about the area. So I am going to star this, because that will give me the area if I plug 50 in where the x's are. So that's 100 and 2 zeros minus, I don't know why I closed my calculator. 50 squared times 2. 50 squared times 2 is 5,000. So the area is 5,000. And check my units. Meters. So the area would be meters squared. The max area is 5,000 meters squared. All right, let's take another look. Yep. It's another fence field type problem. So a rectangular area. Is fenced with 600 meters of fencing as shown. Okay. I don't think I have the picture for this. Let me check to see if it's in the booklet. I'll be back. All right, so I found it right down here. So I just replicated it here, and it'll take 600 meters to do this. So we can let this be x or this be x. Now I'm going to let this be x, which makes this dimension and the one on the top y. Now I'll tell you why in a second. So I've got 3 x's and 2 y's is equal to the 600 meters of fencing. And my area will be length times width, which is x times y, because again, I want to maximize the area. But the reason I picked this side, the double side, rather than the triple side to be y, is because when I go to isolate y, if this was the y, you're going to have to divide by 3 all the way along, and dividing by 3 creates nasty decimals, 0.33333, 0.66666. Dividing by 2 allows you to maintain accuracy if you prefer decimals over fractions. So yeah, you can use 3 over 2, just like you could use 2 over 3 if you divided by 3, but this gives you the opportunity of decimals in case you ever wanted them. So I'm going to continue this question with decimals. And again, this kind of question is something that you could have used or could have done in grade 10, because there's my negative quadratic creating an upside down parabola, which is a maximum. And because I've got my little arrowhead here, this is m, and now it's m prime. Lost my x. So equals 300 minus 3x to the 1, so that's pretty decent. 0 for max mins. X's on one side, numbers on the other. And I get 100. So there are 300 meter sides. And it says, what are the dimensions? So I'm going to take that 100 meters and put it in here to figure out the bottom and top of my picture. Okay, so again, with my therefore statement, I have to be super specific. So I have to say, therefore, there are 3 sides of 100 meters. And 2 sides of 150 meters. And you can totally check your work. 300 meter sides is 300. 250 meter sides is 300. So 300 and 300 is the 600 meters we had in fencing. So you can check your work pretty quickly with some questions. All right, time for a poster problem. They are the thinkers. You may have done these in grade 10 and 11 as well. I'm going to take a little pause, stretch my hand for a sec. Okay, poster problems. So I'm going to draw a poster, but I'm going to do a little color coordination here. I'm going to draw my poster in black. Now you got to think about a poster, and if we were in my classroom, I would point to a whole bunch of hockey posters and tell you how hockey posters or posters in general work. But most posters, I'm going to make my poster like the ones in my classroom, are like that. They could be the other way. But most posters actually have, and I have to make it bigger because I need some place to work, but they have like a little frame of white or black around the outside. Not like a real frame, as in a wooden frame or a metal frame, but just your poster doesn't get printed all the way up to the edge. So I'm going to make my frame rather large. But you have this printed section on the inside, and sometimes there's no writing on the edges of it. Now, sometimes this space is the same all the way around, and sometimes it changes. For this particular question, it says that the margins at the top and the bottom and the sides are 6 centimeters. So this is 6 centimeters, and this is 6 centimeters, and this is 6 centimeters, and this is 6 centimeters. So sometimes that is not the case. Now, I haven't read most of the problem. I wanted to explain what a poster looks like in case you don't have one in your bedroom. So a sheet of paper for a poster contains 240 centimeters squared. So that means this and this, when you do length times width, is equal to 240 centimeters. So my advice is, because you know that information, that you call this and this, the things that make up the 240 centimeters squared, you make that be your X and Y. Because that is an area measurement. It's centimeters squared. So that's area is length times width. So area is X times Y. And that means X times Y is 240. And yeah, I'm going to race ahead and isolate my Y. Now, I still haven't read half my problem. It says, what are the dimensions of the poster if the printed area is to be a maximum? So I want to maximize, and this is my color coding, and I'm using blue because maximizing means derivative. So I need to know the edges of what I'm outlining in blue. So I need to know this dimension, which is no longer X, and this dimension, which is no longer Y. So this used to be X, but it's 6 centimeters in this side and 6 centimeters in this side, so it's X minus 12 centimeters. And yes, I'm taking the derivative of the complicated stuff so that the easy stuff could be what we rearranged. Now, if I do the Y, this used to be Y, but I went in 6 centimeters here, and I'm not printing 6 centimeters here, so this edge, and I'd love to write sideways, is Y minus 12. So what I want to maximize is a different area. And I shouldn't have put X times Y. I should have put length times width. And here's the length. And here's the width in whichever order you feel like. And that is what I want to maximize. So, your choice about whether you want to FOIL this out first or whether you want to plug that in. It's totally up to whether or not you like multiplying fractions. So I'm going to FOIL out first, and with the next question, maybe I'll do it the other way. So X times Y, X times negative 12, negative 12 times Y, negative 12 times negative 12. And now I'm going to put this in wherever there's a Y, because there's no like terms to collect. So there's a y. None here. There's a y. None here. So the nice part is, with this one, this is a top x and a bottom x, so they cancel each other out, and it's just left with 240. Minus 12x minus, 12 times 240 is equal to 2880 over x plus 144. So that's 384 when you collect like terms, minus 12x minus, here's this thing again. Bring that up so we don't have to do the quotient rule. And this is still not the derivative. And this is where you have to keep track of what you've done versus what you haven't done. So I haven't taken the derivative yet. I have made the original look different and different and different until I get to a point where I can take the derivative comfortably, or most comfortably. So time for the derivative. Tell me you're taking it. 0 minus 12 plus 2880x to the negative 2. So 0 equals negative 12x plus 2880 over x to the positive 2. I'm going to take the negative 12x across the equal sign, make it positive, and make it look like a fraction so that I can cross multiply. So I'm going to cross with the x's first. 12x cubed equals 2880. Divide by 12, divide by 12. That should be 240. And remember that when you take the cube root of a number, you have no need to worry about pluses and minuses. So 240 cube rooted is 6.21. So back to the original question. What are the dimensions of the poster? So I know that this is 6.21, so a very small poster. How can that be right? Do you see my mistake? Shoot, I am not starting this all over again. But here's my recommendation to you. When I took the derivative of this, I left the x in. Did you notice that and didn't stop me? That means I am not going to try to gear through this and try to find an answer by fixing all my mistakes. I am going to erase. Before I erase, I want to tell you why I knew that this was wrong. If I have a dimension of 6.21 and I have a margin of 6 and a margin of 6, I'm in negative space, so that doesn't work. That's how I knew I was wrong. So this is my advice. You literally start over. Having said that, if this is a test, you don't erase until you have something better so that I can give you part marks. So then you put a line through that and then start over. So let's do this right this time. I can't believe you didn't stop me. 0 minus 12 plus. That part was right. So I can do the fancy stuff, I can't do the unfancy stuff. Sheesh. So same things, only this time I'm doing it right, and at this point I will not have 12x cubed, I'll have 12x squared equals 2880. Divide by 12, divide by 12. X squared is equal to 240. And this time I do need a plus minus, but X is the side of a poster. So writing down the negative version of this is not going to be at all advantageous. So 15.49, so 15.5, much better answer. So, back to the question, what are the dimensions of the poster? So that means I need to know the red values. So I've got the 15.5 as my red X value. I need my red Y value. So I don't know how to use my memory, as in the one on my calculator. $240 divided by 15.5 is another 15.5, which I kind of guessed. So the poster is actually square. So what are the dimensions? I'm going to say, therefore, the entire poster, as opposed to the printed area, is 15.5 centimeters by 15.5 centimeters. Okay, so this question needed you to maximize the printed area. I am going to guess that the next question is talking about either maximizing or minimizing the whole poster. We'll see. Just a guess. Yep. Find the dimensions of the poster with the smallest area. So I've got my black pen out. I'm going to draw myself another poster. Not very good, mostly because I'm not good with this tablet. So it says the top and bottom margins of a poster are each 6 centimeters and the side margins are each 4. So I'm not going to go to any great lengths to make this to scale, but I will say the top and bottom are 6 centimeters and the side margins are 4 centimeters each. And it says if the area of the printed material, so this space in here, if that area is 238 centimeters squared, it would be to my advantage, because that is a number, to call this X and this Y. I'm going to skip the length times width, so that we have something super tiny to isolate a Y, or if you prefer an X. So, dig out my blue. It says if the area of the printed material in the poster is fixed at 384 centimeters, find the dimensions of the poster. So we need to know this value and this value. So this one used to be Y from here to here, but it's got an extra 6 here and an extra 6 here. So this is actually 12 centimeters longer than the inside. And this one used to be X, but it's 8 centimeters bigger, 4 on each side, than the inside. So that is what I can minimize. So X plus 8, Y plus 12, And I said you could FOIL this out or you could plug this in. So in the last question, I said FOIL out, then plug in. So this one I'm going to plug in, then FOIL out, just so you can see the difference. So the x plus 8 bracket will stay the same. The y will turn into 384 over x and still the plus 12. And now I have to FOIL. So x times 384 over x times 12, 384 times 8, 3072, and that's over x, and 8 times 12. These x's, one top, one bottom, will cancel out, as they would have done if you had done them in the opposite order. Plus 12x plus 3072x to the negative 1 plus 96. Now I'm going to show you something kind of cool. It doesn't really matter if you collect like terms or not, because you're just taking a normal non-product rule, non-quotient rule, non-power of a function derivative. So when you take the derivative, this will be 0, and I won't write it down. This will be 12. Get that right this time. This will be negative 3072x to the negative 2, and this will be 0. So whether you combine them and take the derivative and get 0, or whether you do them individually and still get 0, you will still get the same information for your derivative. Make the derivative equal 0 because that's what you do for all max-min problems. Fix this back up. That's a negative. So I'm going to pull it over here, make it positive. Put this over 1 and cross multiply. Like I've done so many times before, I'm crossing with the letters first and the numbers second. Did that the last time too, didn't I? No, you don't always divide by 12. So, oh crap, 3072 was already on there, divided by 12 is equal to 256. And we have to plus minus square root, just for the practice of it, which means x is equal to 16, because a negative side length of a poster doesn't make any sense. So read the question. Find the dimensions of the poster with the smallest area. So the problem with this question is I just found x. I did not find the poster. I found the printed area. So we will have to come back to this in a second. I still need to find y. And you find y the same way, as always. So 384 divided by 16 equals 24. So a lot of people will write down that the poster is 24 centimeters by 16 centimeters, but that's actually not the case. And the reason it's not the case is because the poster is x plus 8 sideways, the way I've drawn it, and y plus 12 on the up and down, the way I've drawn it. And x isn't the same thing as x plus 8. And y isn't the same thing as y plus 12. So x plus 8 is 16 plus 8, which is 24. So now I know how wide the poster is, not the printed area. And y was 24, so 24 plus 12 is 36. So now I have the answer to the question, which is therefore the poster is, and you can say it any way you want, 36 by 24, 24 by 36. Actually, I should be more specific with this one. It was 36 centimeters tall and 24 centimeters wide. And the reason I'm making a big deal about this is because the border was not the same all the way along. So the x plus 8 was this way, and the y plus 12 was this way. All right, booklet. That's funny too. Field problems, number 3 to 12. Poster problems, 7 to 12. So because I have it out, number problems are here, field problems are here, poster problems. Revenue problems, three-dimensional box problems, travel problems, miscellaneous. And you will get down into miscellaneous and you'll think, oh, she didn't assign any of these, but I highly recommend looking at these. And the reason I recommend looking at them is because, as I said at the very beginning, I've decided to break these up into types. But there are some people, teachers, professors, who will say, oh, well, if I showed you one kind, you should know how to do all the rest of them. So now you may be a complete pro at number problems and field problems and revenue problems and three-dimensional problems and travel problems and the poster problems. And then you might get it down into miscellaneous and go, holy smokes, I don't have a clue what's going on here, because every type is different. So don't be afraid to look at these and ask, or don't be afraid to get in touch with me in the future. So back to this, just so you can see it. And we are done. Max Min, congrats to you. And a bigger congrats to me.